Chapter 3, Exercise 14. Assume that f and g are functions. Part A, show that f intersect g is a function. Part B, show that f union g is a function if and only if f of x is equal to g of x for every x in the domain of f intersect the domain of g. Right, so in this question, we're just going to apply the definition of a function several times. So we should have that very clear. And just to restate what a function is a function is a single valued relation. Now, just to remind you, a relation is a set of ordered pairs, and a single valued relation is an ordered pair x comma y, such that for every x in the domain of f, and remember the domain is pretty much just all the things on this left-hand side, or this left part of the ordered pair, there exists a unique y such that this ordered pair x comma y is in the function. So essentially it's just your probably innate understanding of a function that f of x is equal to y, and for all, z that are not equal to y, f of x does not equal z, right? Essentially, a value at a function can only take one value at any point. That is what I'm trying to say. Okay. With that said, we're going to use the more set theoretic construction because this is a set theory textbook after all. So, yeah. We'll see. You'll see. Okay. So, to show that f intersect g is a function, we have to show two things. We have to show that f intersect g is a relation, first of all. And second, we have to show that this relation is single valued. Alright. Let's move this, banish this to the shadow realm, and let's get started with the relation. So, let's suppose z is an f intersect g. Then z is in f and z is in g. And since z is in f, then z is equal to xf comma yf in f. Similarly, z is in f implies that z is equal to xg comma yg in g. So one of these is enough to show that z is a relation. Whichever route you take, either you want to pick f or you want to pick g. I just showed both for your convenience. Z has to be, if z is an f, right, and g. I get those two mixed up. Okay. So if you pick z and f, then z is a relation. Z is an ordered pair. If you pick z and g, then z is an ordered pair. So no matter what you do, z has to be an ordered pair. And since the only thing we assumed about z is that it is an element of f intersect g, then f intersect g must be a set of ordered pairs and a relation. In other words, move this, put our connector in there, and there. That's part one. And now, oh my god, almost got it exactly right. Okay. Now we have to show that f intersect g is single valued. So what does this mean? We must show that if x is in the domain of f intersect g, then it has a unique y in the range of f intersect g such that x comma y is an element of f intersect g. So I'm going to write it out. So x in domain f intersect g implies that there exists unique y in the range of f intersect g such that x comma y is in f intersect g, or that f of x is equal to y. Oh yeah, that's one too many parentheses. That's just what I'm trying to say. It might be clearer written out this way. Actually, just so that you don't get too confused, this is what the assertion looks like. We're trying to prove that assertion. So now we're going to suppose x is in the domain of f intersect g. Then just by that virtue, then there must exist some y in the union of the f intersect g such that, or rather, some y in the range of f intersect g such that x comma y is in f intersect g. Right? Now, what do we want to show? We want to show that this y is unique. So let me rename this variable to y1. And now let's assume for the sake of contradiction that there exists y2 in the range of f intersect g such that x comma y2 is in f intersect g. Okay, so how do we go about showing that y1 is equal to y2? This is our new goal. We're going to show that if you pick a supposedly different y, then there's still going to be the same y. That's how you show something is single valued. Okay. So, x comma y1 being an f intersect g implies that x comma y1 is in f and x comma y1 is in g. Either one works. All we're going to use is the assumption that f and g are functions. So whichever route you want to take from this point on, it's going to be the exact same proof. I, for one, am going to take f, since it's closer to the left. Right. Since x comma y1 is an f, then x is in the domain of f, and y1 is in the range of f. Now, what you could do here is simply conclude that since this pair isn't a function, then y1 must be single, or rather, and the function is single valued, then y1 must be unique for this choice of x. But that's not quite as interesting as the proof we've set up so far, and I feel like it's a bit hand-wavy and wishy-washy, which I'm not a fan of, so we're going to go through the whole thing. Now, similarly, since x comma y2 is in f intersect g, then x comma y2 has to be in f. Thus, x is in the domain of f, and recall that this x is the same thing. This x is the same as this x, right? And y2 is in the range of f. Okay. So f of x is equal to y1 and f of x is equal to y2 by transitivity. Y1 must be equal to y2, right? But we assumed initially that y1 is not equal to y2. So this is a contradiction. And then our only way to resolve this is to accept the fact that f intersect g must be single valued. Right? So just to recap, what we're trying to show is that f intersect g is single valued, for which we assume that it is not single valued. So what we assumed implicitly is that there exist two different y's such that x comma y1 and x comma y2 are both in f intersect g, right? Oh my god. And y1 is not equal to y2. How could I forget that? Okay. I'm sorry if that confused someone, right? So what we assumed is that there exists a different y, a y that is not equal to the original y we picked, such that the two different pairs were still in the set f intersect g. But then what we showed is that given that f or g are functions, that these two supposedly different values must be the same. So there you go. That is our proof. And thus f intersect g is single valued. So it's a single valued relation, meaning that f intersect g is a function. Okay, cool. Now for part B, we have to show that f union g is a function if and only if f of x is equal to g of x for every x in the domain of f intersect the domain of g. Okay. So, how are we going to do this? Okay. So we need to show both ways. We need to show this implies this and this implies that. Right? So hold on. This is A, this is B. Okay. Right. So that is how I proved it. Alright. Now this is what I'm going to do. Proving it this direction. So proving that f union g is a function implies that f of x is equal to g of x for all x in domain f intersect domain g. I don't know why I found that to be somewhat challenging, so what I did was use a proof technique known as a proof by contraposition. So if you've done some logic before, you will know that A implies B is the exact same thing as not B implies not A. It is also the foundation, if you will, for a proof by contradiction. It's the same idea. So, taking this left-hand side to be A and this right-hand side to be B, what I'm going to do is, instead of showing that f union g implies that being a function implies that these are equal for every x in the intersection of the domains, I'm going to show that if this is not true, then this can't be true either. Right? So let's do that. Now assume that f of x, that it is not the case that f of x is equal to g of x for all x in domain f intersect domain g. Right? Now, how do we express this mathematically? So it's going to be something like not for all x in domain f intersect domain g, f of x is equal to g of x. Right? And now this is logically equivalent to saying that there exists some x in the domain f intersect domain g such that it is not the case that f of x is equal to g of x, which itself is logically equivalent to saying there exists some x in domain f intersect domain g such that f of x is different from g of x, right? So what are we doing now? We're going to assume that there exists some value of x in the shared domain such that the outputs of these two things are different. F of x and g of x are different. And show that that implies that f union g is not a function. Right? So, we assume that there exists some x in the domain of f intersect domain g such that f of x is not equal to g of x, right? Now, set theoretically, we can write this as there exists some x in domain f intersect domain g such that there exists some y1 in the range of f such that x comma y1 is an f, and let me move this down. There exists some y2 in the range of g such that x comma y2 is in g. And y1 is not equal to y2. Give me 1 second because I messed up the scope of these things. Here. And here. Yeah. It's a little less readable. But this is the correct way of writing it. Now, this is just if you're very pedantic about scopes, but I know that I am I am very pedantic when reading someone else's proof. So I have to do it myself too. So there exists some x in the shared domain such that there exists some y in the range of f, and there exists some y2 in the range of g, such that this pair x comma y1 is in f, and this other pair x comma y2 is in g, and they're not the same. Now the error before is that in the previous way I wrote it, this y1 and y2 were outside of the scope of these existential quantifiers, but that is a nitpick, honestly. I don't know, some of you might have caught it. If you didn't, that's perfectly fine. It's just for like really annoying people like myself. Okay. Right. So, this is our assumption, right? Now, if indeed x comma y1 is an f, then surely x comma y1 is an f union g, as f is a subset of f union g, and similarly x comma y2 is in g, implies that x comma y2 is an f union g for the exact same reason. So what? X comma y1 being an f union g implies that x is in the domain of f union g, and y1 is in the range of f union g. Same as saying that f comma y2 being an f union g implies that x is in the domain of f union g, and y2 is in the range of f union g. Now notice this implies that for some x in the domain of f union g, there exists y1 in the range of f union g, such that there exists some y2 in the range of f union g, such that x comma y1 is an F union G, and x comma y2 is an F union G, and y1 is not equal to y2. Now, if you've been following along, this means that F union G is not single valued. Right? Essentially, F union G of x is equal to y1, and F union G of x is equal to y2, and y1 is not equal to y2. So F union G of x is not equal to F union G of x, which is a silly thing to say. So F union G cannot be a function. Right? Thus, for all x in domain F intersect domain G, f of x equal g of x implies that it is not the case that F union G is a function. And now equivalently, F union G being a function implies that for all x in dom F intersect dom G, f of x is equal to g of x. And there we go. That is our first part of this proof. Right? So, what's next? What's next is that showing that if f of x is equal to g of x, implies that F union G is a function. Okay. Now, for this one, what I did was consider that there are three cases, or let's see. I'll get to it in a second, right? So we want to assume that this really long assertion, or this really long formula, is true. And then we want to show that F union G is a function, right? Now, we have to show that F union G is a relation and that it is single valued. Now, F union G is... We already kind of did this work for relation in the previous part of this video. So I'm just going to argue that F union G is the union of two functions, meaning that they are relations. So F union G must also be a set of relations. Right? I think that one is pretty self-explanatory. And then now, showing that it is single valued is a bit less obvious. It's not quite as straightforward. So, suppose x comma y is in F union G, right? Then we know that x comma y is in F minus G is in F or x comma y is in G or x comma y is in F and x comma y is in G. Right? Oh, wait, no, wrong type of parenthesis. Okay, so these are the three cases, right? Now, this has to be like an exclusive OR. But the idea is it's either only in F, or it's only in G, or it is in both. That is how we get that x comma y is in F union G, right? And more explicitly, x comma y is in F minus G, or x comma y is in G minus F, or x comma y is in F intersect G, right? Now, what's nice about this is, oh my god, give me the new page, thank you, is that we already did this case. So, by part A, by part A, F intersect G is a function. So, x comma y is single valued. Or, essentially, what I'm saying is we don't need to care about this part. Actually, this is wrong. A pair is not single valued. So we only need to check F minus G and G minus F. Alright, so, man, this video is taking a lot longer than I expected. So, if x comma y is in F minus G, then x comma y is in F and x comma y is not in G, right? And what we want to avoid explicitly is that we want to avoid this scenario. Right? Where you have one pair of values in one function and a different pair of values, both sharing the same x, but they give you different results, right? So this would give you f minus g of x is equal to y1, and g minus f of x is equal to y2, right? Which is perfectly fine. But then when you put them together, oh, and I keep forgetting that I have to add this extra clause, and y1 is not equal to y2, right? This leads to f union g of x is equal to y1, and f union g of x is equal to y2, which implies that f union g of x is not equal to f union g of x, which breaks everything pretty much. Okay. So there's that, right? So what I'm going to show is that this can't ever happen, right? So suppose there exists some, or rather, suppose x comma y is an f union g, and specifically or rather, no, we already assumed that, didn't we? Yeah, we already assumed this. So now let's suppose x comma y is in f minus g. Then x comma y is in f, and x comma y is not in g. Now we assume, for the sake of contradiction, that there exists some z not equal to y, such that x comma z is in g, right? Or rather, more specifically, even g minus f. Okay. Now, x comma z being in g minus f implies that x comma z is in g and x comma z is not in f. Now, these don't matter too much. What we really care about is this right here, right? Because x comma y being in f implies that x is in the domain of f, and x comma z being in g implies that x is in the domain of g. So x is in the domain of f and x is in the domain of g, which implies that x is in the intersection of these two sets. Okay, cool. So that's getting us somewhere, because by assumption, for all x in domain f intersect domain g, actually, you know what? We don't even need to add this. I remember why I forgot it now. All we need to show is that y1 is equal, or sorry, that x all we need to show is that y is equal to z. Okay. Okay. So by assumption, every x in the intersection of the two domains has the same value both for x and for g. Now this means that y, which is equal to f of x, is equal to f of x, which is equal to g of x, which is equal to z. And thus, by transitivity, y is equal to z. So, f minus g, or rather, so for all x in the domain of f union g, there exists some unique y, such that x comma y is in f union g. Right? No matter how you split it, you get the same result. And this is the other case where x comma y is in g minus f is analogous. It's basically just flipping or changing the symbols and you get the exact same proof. I usually would do it, but I'm really tired today, so I'm not going to. Okay, so this means that f union g is a single valued relation. Thus, f union g must be a function. So indeed, for all x in dom f intersect dom g, f of x equal to g of x implies that f union g is a function. Now we conclude that f union g is a function if and only if for all x in domain f intersect domain g, f of x is equal to g of x. Okay, so there you have it. That's all of exercise 14. Hope this was helpful. I apologize for the bad handwriting. I'm just really tired today. But we got through it. That's all that matters. Alright, I hope this was helpful. I will see you in the next video. Bye-bye.